So atoms make bonds because in doing so, the energy electrons goes down. The energy electrons goes down because electrons in a bonding orbital have lower energy. So this is crucial, as we've already said. So bonding molecular orbitals have lower in energy. But the question is, why is that? I mean, why are the electrons lower in energy than the bonding orbital? And the fundamental reason for that is simply because the molecular orbitals and molecules are larger. So if they're larger, that changes the wave properties of the electrons in those orbitals, obviously. And the electrons have effectively longer wavelengths in the larger orbital. This is much like, imagine a wave on a string. You know, if you make a guitar string longer, then the note, the sound when you pluck it is lower because the frequency is lower because the wavelength is longer, right? It's the same thing. So electrons have longer wavelengths, and because wavelength is related to momentum through the de Broglie relationship, so let's just go straight to these equations. So if we have a larger orbital, we have a longer wavelength. That's the wavelength, this Greek symbol lambda, we've seen that before. So if I have a longer wavelength, this means the momentum must be lower because wavelength is reciprocally related to momentum. And if the momentum is lower in both of these equations, Ke meaning the kinetic energy, is lower also. So a larger orbital means a longer wavelength, which results in lower momentum, which results in lower kinetic energy. And fundamentally, that's the most important reason why the energy electrons go down when they get into a molecular orbital. Larger orbitals, lower kinetic energy. As we've seen, in the bonding orbital, in fact, let's draw a sketch of it. So here's a sort of representative sketch of the wave function of a 1s atomic orbital, for instance, on a hydrogen atom. And if we draw the same sort of sketch of the wave function for the 1s bonding molecular orbital, for instance, for molecular hydrogen, then it's going to look sort of schematically something kind of like this. So obviously this one is larger, whereas the atomic orbital is smaller. And remember the wave function squared. The wave function squared gives us the probability of finding the electrons. And so if we draw a sketch of the wave function squared, difficult to do accurate. This is a schematic representation of this. It's even larger in between the two nuclei. So that implies that the highest probability of finding the electrons is between the two nuclei. And that's also beneficial because that allows each electron to interact with two nuclei now instead of one. There are the two electrons in their most probable position. And so that allows each electron to interact with two nuclei, which is good, right? Because if the positive charge stabilizes a negative charge, then there's two of those. Also, the electrons are most likely to be found in between the two nuclei. That allows the positive charged nuclei to get close to each other without the two positive charges repelling, because the negative charge in between the electrons shields the two as well. So we also get shielding of the nuclei from one another, all as a consequence of the shape and the nature and the wave properties of this bonding molecular orbital. So the bonding molecular orbital has the right shape to allow the nuclei to approach each other and shielding. It also has lower kinetic energy. We don't have to worry too much about putting these two electrons together, raising the energy, because the motions of the electrons are correlated in such a way that they don't never get exactly on top of each other. So that's not a big thing we have to worry about. And instead of being a problem putting the two negative charges together, that's close to each other, that's a good thing, because that's what allows the two nuclei to get close to each other. So this is the reason why putting the electrons into these bonding molecular orbitals is a good thing. It's why atoms do it. It's why atoms make bonds. It's why we have molecules. Lower kinetic energy, better electrostatic picture as well. So what's going on with the anti-bonding orbital? Two atomic orbitals must make two molecular orbitals. If a bonding orbital is formed, an anti-bonding orbital has to be formed exactly the same time, whether we like it or not. Okay, hydrogen molecule is smart enough not to put any electrons in that orbital because it's high in energy. Aufbau told it to do that. But let's have a look at it again. So if this is a sketch of the wave function of the 1s atomic orbital, this would be for atomic hydrogen, and a sketch of the wave function for the sigma star anti-bonding orbital for molecular hydrogen. Then what does it look like? So this time we have to show the phase information, and we're going to represent phase by shading one of the orbitals. Remember, don't really like using positive and negative. That implies charges which aren't there. And so what we find is there's a node, in fact more exactly there's a plane node in this case, exactly between, and that node comes exactly in between the two nuclei. What that means is if we generate the wave function squared for the anti-bonding orbital associated with hydrogen, that means the probability of finding the electron directly between the nuclei is 0. So an electron in the anti-bonding orbital cannot possibly shield the two nuclei. This is a very bad situation, and that's why an electron in that orbital, or certainly an electron pair in that orbital, would be higher in energy than they would be had they not formed a bond at all. So molecular hydrogen has this anti-bonding orbital. It doesn't have any electrons in it, and students often ask, how can it be that this orbital is there? I mean, what does it mean? Well, remember, if the electrons have the property of wave and they overlap, the waves must overlap two different waves, must make two orbitals, that orbital is there. It's there in the same sense that a hydrogen atom has a 2s atomic orbital. It just doesn't have any electrons in it. The molecule has the anti-bonding orbital. It just doesn't have any electrons in it because the two electrons are in the bonding orbital, and in that orbital, they are lower in energy.